Need to talk about is, so if I give you the graph of y equals f of x and y equals f prime of x, we should be able to understand the differences between what a function's graph gives us and what a derivative's graph gives us. If we graph the derivative, not the function. So yeah, it's a series of numbers. But when we graph y equals f of x, what we're doing is plotting points. When we graph y equals f prime of x, we're plotting slope. So I'm going to put a little picture here as an example. So if I graph y equals x squared, those are the points that satisfy the equation y equals x squared. Yes? Okay. The derivative of this, so if I say the function is x squared, its derivative is 2x. It's earlier in your notes. You can go look and see that it is. If I plot the points for y equals 2x, and if I'm not a complete chump about it, when x is negative 2, y is negative 4. 1, 2, 1, 2, 3, 4. When x is negative 1, y is negative 1, or negative 2. When x is 0, y is 0. When x is 1, y is 2. When x is 2, y is 4. Tell me about the slope of this part of the parabola. Yeah, it starts with big negative slope up over here. Big negative slope, smaller negative slope, smaller negative slope, smaller negative slope, no slope, no slope, big negative, so negative slope. No, not the line. I'm not talking about the slope. I'm talking about the coordinates of the slope graph, of the derivative graph. So if you're below the x-axis on the derivative graph, that means you have negative slope on the original function. As you go to the right, tell me about the slope. It's small positive, and then more positive, and more positive, and more positive, and bigger positive. Look at the y-coordinates on the derivative graph. What happens? High, but it's not the slope we're talking about here. High x, y coordinates. So really positive slope here, like here, it's got a really positive slope. Over here, it's got a big positive y coordinate. Okay? Interesting? Mm-hmm. Okay, flip the page. So we're going to do this. I'm going to draw a function here, and then I'm going to ask you to draw its derivative graph. That will be boring. Do, 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 do. Okay, so I'm going to give you those points so we can just join them in a curve. And then I'm going to just well, that's awful. Okay, we'll draw that at the end just for kicks and giggles. Okay, so this is y equals f of x. Got that drawn-ish? So what I'm going to do is we're going to work from left. I'm going to do what you're going to do. So we're going to work from left to right. And you're going to tell me the slope of those points. Now, you should actually do all of the points, so every single little one of them, all infinite number of points. Really, Mr. Ab? Really? Okay, anyways. So, slope at the first point is 0. Slope at the first point is? Slope at the first point is? Next point is 0. Slope at the next point is 1. It's rising, run, and running 1, so it's got a slope of 1. Slope of the next point. Yeah, but from here to here, it's just rising 1 and running 1. What's the slope? 1. Slope of the next point. Negative 1. Slope of the next point. Slope of the next point. Slope of the next point. Negative 1. Okay. Slope at... So we're going to talk about from here to here. So from here to here, the slope is small and positive, really big and positive, and then as it gets to the bump, it gets really small and positive. Would you agree to that? Small positive slope, really big positive slope, small positive slope, no slope. So this is where you kind of have to go, what? So small positive slope, really big positive slope. I'm guesstimating here. Small positive slope, small positive slope, small positive slope, small positive. Oh, good. And then talk to me about the slope from here on. What? Really small negative and then really big negative really fast. So if I join up all my blue scribbles, the curve looks like this. Tell me about right here. I've got some extra spots that I have to talk about. Tell me about the slope right here, in where that yellow is. Yeah, but tell me about, notice I didn't talk about the graph right in here. Tell me about the slope. It's 1, so it's got to come back. Ah, there's an open circle there. And tell me about the slope from here to here. It's negative. It's not on the graph. I need to chew. Open circle. And then the slope here. We'll close that one in because we're not quite too sure about it. And there's the curve. That's the graph of the derivative. Yeah? Weird? Yeah, a little bit. Okay, let's do another one. I won't be as weird this time. This one's just going to be an ish drawing. So there's no points marked on this curve. Yeah, do it on the bottom of the same page. Yeah, because the other one's the other way around. So tell me about the slope from this point left. No, it isn't positive. It starts off big negative and becomes 0, small negative, and then 0. Starts off big negative, and eventually it will become 0. Tell me about the slope between the next two yellow marks. Little positive, big, little positive, big positive, little positive. What's it got to look like between those two yellow marks then? Do that again. It's got to be low, really high, and then really low. Okay, join that up with a nice smooth curve. Low, really high, really low. Tell me about to the right of that yellow mark. Starts off really flat, really low negative, and then drops off the page. And then drops off the page. Notice I didn't ask you what the slope is. It's really impossible to do that. You'd have to get all physics 11 on it and draw those tiny little triangles and say, Mr. F, right here, I draw a triangle. It's got a slope of drops 4 and runs 1. And then you come down over here and this coordinate's got to be like -4. Do you really want to do that? No, this isn't physics 11. But do you remember doing that? Oh, okay. Now it does make sense what I meant by the triangles. So that's all, actually what physics 11 is making you do is taking a position time graph and plotting and creating a velocity time graph. And all you're doing is going, and then the slope right here is -2, and it runs 1. So yeah, that's why the coordinate right here is like -2. Yeah. I know I'm making fun of you a little bit. No, not so much. But you get the idea? What we're doing, we're going from left to right. We're looking for the key features of the graph. Do I notice I didn't ask you about the x-intercepts of the graph? The derivative, when you plot the derivative, you don't really know. That information is lost. The only information that can be maintained from original function to a derivative function is slope. And by that, you also pass along the information of where the maximums and minimums are. Okay? Did you notice that the maximums and minimums become x-intercepts? That's something to notice as well. Maximums and minimums become x-intercepts. Pardon me? Yeah. But you don't need, yeah. So things to notice. Derivative graph will only show slope. F prime of x only shows slope. Shows slope. Maxes, mins become x-intercepts. Pardon me? No, it's just me indicating. It's just arrows. I'm just trying to show you that information, where those points move to. Okay? Okay. Going the other way. So graphing y equals f of x from y equals f prime of x. So we're going to start with, I don't know, we'll start with a physics 11 kind of thing. So you get in your car and you drive a certain distance, and then you stop. Sorry, you accelerate. Yeah, that's what we're doing here. Y equals f prime of x. So we hit the gas and we rapidly move away from somebody's house. and then we sit there, and then we hold the gas at the same, hit the cruise control, and then we come to a stop. So this is a velocity time graph, I guess. So there are three main parts of this graph. Duh. Tell me about the y-coordinate right here. It's 0, yes? So I'm saying the slope right here is 0. Tell me about the y-coordinates from here along to here. Small positive to big positive. So what I need to do is to draw a graph that's got no slope to a really big positive slope. Well, I don't know. It depends the scale of the graph. I'll say big, but big's a relative term. So I want you to draw a curve that starts with no slope and goes up to big positive slope. And I've already seen somebody do it once in the air with your finger, so I'll replicate what I saw. I saw something that looks like this. No slope. Oh, wait. Does that blue dot need to start there? No, that blue dot could be up here. It could be down here. I don't know where it is. Okay, so don't assume that dot's going to. So let's not put it there because I don't want to make that an assumption. So that blue dot could be anywhere along that line, anywhere along that axis. So I want small positive slope. Sorry, no slope. Nice flat bit, and then climb. Woo! Isn't that fun? Now tell me about the slope from here to here. It's the same. Tell me about graphs. Tell me the type of function that has I almost said it. A shape that has the same slope all the time. A linear, yeah, and it's going to have, like that's like 5. So it's got to have the slope of 5 the whole time. So maybe I should have started this. Maybe I'll fix it a little bit because Leah just noticed. She didn't know what she noticed, but she noticed that I was noticing that she noticed that I noticed that perhaps I was going a little bit too extreme in my climbage. So maybe it does this to here. And then it's got a slope of 5 the whole time. There. It is fun. Okay, oh, got a little excited. Drew that a little far. That's better. Okay, tell me about the slope of the third part of the graph. Big positive to little positive to 0. Now, am I going to fall here? This is where kids start to make mistakes. Am I going to fall here? No, I'm actually going to climb more, but not as fast. So I'm going to climb a lot early, and then I'm not going to climb as much late. Can anybody guess what that's going to look like? I'm going to climb a lot early. Oh, good. Yeah, climb a lot early and then not as much late. Cool. Hard? Do you think the derivative graph's a little bit harder to do? Going the other way to graph the original function? I think that's a little bit harder to do. Where you have to go, what's the slope telling me? Or, sorry, what's the coordinates telling me? It's telling me slope. It's not telling me. I think this is harder to do. Is it? Okay, I've got a couple of no's and some yeses and some misrep. I guess it depends on how you look at the world. Okay. Flip the page. Or you're already on the other page. One more. Yeah, you better believe it, sister. This is fun. I like this. We'll just do a little one here. There. So this is y equals f prime of x. So we start with somewhat of a large negative slope-ish, right? All the slope right here to the left of that blue mark, we agree that all the y-coordinates are negative, so all the slopes are negative. So I'm saying that you're falling. You're falling a lot early and then not so much late. No, but it's not. No. But I mean, right here, the y-coordinate could be like -4. So I want you to draw a curve that has a slope of -4, and then a curve, and it has a slope of -3, and then a -2, and then a -1, and then finally a slope of 0. No, because this is position, you can't really jump in space. But you could do this. You could start with a large negative slope. Yeah, but when I graph derivative graphs, I have to jump. Going the other way, you won't jump. That was bad, because this is you. Okay, so you jump out of an airplane. You're falling really fast. You pull the parachute. Right? You come almost to a stop. Well, you do come to a stop with this parachute. It's super powerful. And then you engage your rocket boosters. You start to climb. You climb a little bit. Now, what about right here? Do you climb still? From here to here? Yeah, but not as much. You know what I mean? You're going to climb a lot early. And then as you go from this point to this point, it's almost like your boosters are running out of fuel. You're going to climb like this to about here. Tell me about the slope from here down into here. No, the other way around. Yeah, small negative to big negative. So, oops, there's a problem. The fuel runs out of your rocket pack, and some schmuck cuts your parachute. And well, you want to put one there? I'll put one there that has. Sure? Okay. Well, just draw a big line. Yoink. These are actually easy to go the other way with. So if we started with this is our graph. There, we'll just do this as our graph. So we've got a positive constant slope and then a negative constant slope. Positive constant slope and then a negative constant slope. That's all it is. Gonna be good? See how that's working? Okay, so that's the derivative. That's the derivative graph and how we do it. It's kind of intuitive. You know what I mean? You gotta have a feeling for what's going on. You don't ever get your little triangles out and measure. If you do, I might heckle you. Unless you guys want to do a lab. You guys want to do a Physics 11 lab and get the ticker tape out? And I'm getting a no. It's death? Oh. Okay, so no ticker tape. Okay, flip the page. Diffusibility. Did I? Oh. What happened? It's not here. Oh, there it is. Oh, I'm an idiot. Mr. App, don't call yourself an idiot. Okay, the right-handed derivative. Oopsies. As x approaches right hand. A from the positive. I guess I should draw a picture too, just so everybody knows what I'm talking about. A from the right, f of x No, I don't want to do it with A from the right. I want to do H. Sorry, I am not an A person. So a right-handed sided derivative looks like that. If I want to do the right-hand side derivative of A, all I'm going to do is take out the x and put in A. So graphically, what I'm saying is this. So I've got some funky function that stops at A, and I want to know the slope right there at A. So I can, would you agree that I can't talk about the slope on the left-hand side of A? So that's why we have to call it a right-hand derivative, because I can only approach it from the right. Because there's no left. Ah. Left-hand, right-hand derivative of A, let's change it to B so we see it. So f prime of B would be the limit as h approaches 0 from the left of f of B plus h minus f of B all over h. So right here, that would be B. Okay? Ooh. Okay. Now this is where it gets a little funky. The following function, nice spelling, has left-hand and right-hand derivatives at 0, but no derivative there. Okay, I'm going to draw the function. So the graph of this function looks like this. X squared when x is less than 0. So tell me the slope right here. 0. So what do we want to say? The limit as h approaches 0 from the left of f of x, it's 0. Okay. Tell me about the slope of the, I don't want to use black, that color. Tell me about the slope of that function. The limit as h approaches 0 from the right of f of x. It's, tell me what the slope of that blue graph. It's 2. It's positive. It's 2. So show the function as a left-hand derivative. It does. It's 0. A right-hand derivative. Yes, it does. It's 2. But it doesn't have a derivative. The derivative doesn't exist there. But try and draw a tangent line there. Try and draw a line that just touches that point and represents the slope of the curve at that point. Can you do it? But you can't, because the slope is changing from 0 to 2 instantaneously. If I draw the derivative graph over top, which I probably should do, the slope is large negative, and then it's flat. Large negative, and then no slope. And tell me about the slope of the right-hand part of the graph. It's 2. Tell me about what happens. What does it create on the derivative graph? Jump. Jump, 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 jump. Okay. So when you see rapid changes in slope, or instantaneous changes in slope from one point to the next, that is bad. Okay? Creates jump discontinuities. Jump on derivative graph. Okay? Cool? Yeah? Okay. You know what? I'm going to stop here. So that takes us to the end of 3.1. In class today, we're going to talk about 3.2. And 3.2 is, when are you allowed to take the derivative? Okay? 3.2 talks about continuity. So, all the types of discontinuities from chapter 2 that we talked about. And then I'm going to add in some new points that are just as exciting. Like this one we just drew here. Okay? Those cause problems. We don't like problems. We like solutions. Okay. That's it.